Hello everyone. So this is the second part of the complex numbers lecture. The first one you can find in my YouTube channel, of course, as usual. And if you are following me from YouTube, or if you found this video from YouTube, please don't forget to check the channel and subscribe. Okay, let's start. So in the second part of the complex numbers, we said that we are going to talk about the forms of complex numbers. There are a few forms of complex numbers, and most of them are very easy to deal with, and it's very easy to convert from one to another one. Oops. Okay, so let's start. So I will still go through the notes, but I will summarize the whole thing while I am doing so that we don't get confused over the whole file. Okay, how do I write a complex number in modulus argument form, or we call also this a polar form? Well, we know that the complex number could be written as the following. The general notation for the complex number is z, and we write it as a plus I times b, or you could, or b times I. It's the same thing. And this part would be our real part, and this part, b, would be our imaginary part. This is our so-called Cartesian form. So the first form of the complex numbers is called the Cartesian form, and it's the usual form of the complex number. It's how we defined it as well. So this one we call as Cartesian. The second form that we are interested in is called the modulus argument form, or the so-called polar form. In order to convert, or let's say in order to be able to write a complex number in this form, we need the argument and the modulus. Well, we already know what's the modulus. So R is defined to be the following. So let's say here, I will delete it later. It's denoted by the absolute value notation. So two lines, and this is equal to square root of a square plus b square. Right? So this is our modulus. That's fine. And the argument would be the angle that the vector in the Argand diagram makes with the x-coordinate. What it means, if you draw your Argand diagram, okay, and if you find your complex number, let's say it's this point here. So this is your A, this is your B, and then you draw a vector from the origin to this point. Then this angle here, let's say theta, will be your argument. We usually write as simply, it should be somewhere here, well, we usually either write arc of z, or we just call it the argument. And we call this theta, of course. This is the angle that this vector makes with the x-coordinate. Okay, so these are the two things that we need in order to be able to write our modulus argument form. And it is written in the following way. So we say that z is equal to r times cosine of theta plus I times sine theta. And that's all. That's our modulus argument form, or the so-called polar form. As you can see, we only need to know our modulus, which is r, and our theta, which is our argument. Okay, let's move on. There are some notes here about the angles, about the domain and the range. Well, we all know that the sine and cosine are trigonometric functions with the period of 2 pi, right? So if question specifically asks you to write your angles in certain domain or certain range, then make sure you subtract or add 2 pi as many times as necessary so that you can range your range or the domain. Well, this is the summarized part, all of this part that you see here. Okay, summarized version. So let's move on. Let's see what important details we have about our modulus argument form. The one quick note about this is that it's also written as in the following way: z equals to, I think it was written as the following. So you call it r times cis c theta. So what this refers to, c for the cosine, s for the sine, and I for the imaginary number. So you could also see the form in this form. We call this CIS form, but it's essentially the same thing as the modulus argument form or the polar form. There is no difference at all. Okay, Let's see. Yes, as we see here, that's what they say. It is often written as z equals to r times cis theta. So it's also a modulus argument form, but sometimes they do call it cis form. But yeah, essentially they are the same thing. It's just abbreviated. Now let's look at this important detail that says the complex conjugate of r cis theta is r cis minus theta. So if you want to find the complex conjugate, it's sufficient to just have a negative angle, and that would be all. Okay. Let's have a look at how to multiply complex numbers in modulus argument or the polar form. Well, there's only one important detail that you need to know when you multiply two complex numbers in this form, and that rule is that when you multiply two modulus arguments, or let's say when you multiply two complex numbers and find their modulus argument, that's the same thing as multiplying their modulus argument separately. Okay, that's the first thing. The second thing is that if you multiply two complex numbers and find the argument of this multiplication, then it's sufficient to find the argument of the first one and the argument of the second one and just add them. Okay, so with these two information, it's already possible to find them to multiply two complex numbers in the polar form. Let's see, we also have an example for this, and we will see how does this work. But important is that we remember that these two rules while we multiply two complex numbers in this form. Okay, let's see what else we have. How do I divide complex numbers in modulus argument polar form? The same idea when you divide two complex numbers and take the modulus argument. That's the same thing as finding the modulus argument for each one of them and then dividing that result. Okay. And if you divide two complex numbers and find the argument, and that's the same thing as finding the argument of the first one and the argument of the second one, and then subtracting these arguments. Okay, and this is two important rules for the division in the polar form. Let's see an example. Okay, it says here that, okay, so we have z1, which is 4 root 2 CIS 3 pi divided by 4, and then you have Z2, also written in the polar form, but not abbreviated. That's fine. And then says find Z1 times Z2, giving your answer in the form of R cos theta plus I sin theta, where your theta should be between 0 and 2 pi. Well, since we are multiplying two complex numbers in the polar form, as we said, it's sufficient to multiply simply your modulus arguments. So 4 root 2 times 2 root 2, right? Because root 8 is the same thing as root 4 times root 2, which is equal to 2 root 2, right? Okay, so it's sufficient to multiply root 4 2 with 2 root 2 and then add the angles. So first you have here 3 pi divided by 4, and then you have a pi divided by 2 here. But pay attention, there's a minus here. So, and that's not what we want. We know that in the modulus argument form, we have a plus. So it should be cosine theta plus I sin theta. So how do we change this minus to something positive? Well, this is a very important detail here. Well, we can do the following. So, well, as you see in the screen, so you can take the angle, the angle that you have here inside, because this will be the complex conjugate. And then you can basically continue with the same process. Okay. Okay, so let's continue. Also, it's because of the angle, I would say here, but anyways, so let's move on. So we have a minus p divided by 2, and we have 3 pi divided by 4. So we add these angles, and then we get p divided by 4. Of course, the multiplication for root 2 and 2 root 2 gives you 16. So your answer is 16 CIS p divided by 4. But you have to write it in this form. Okay, 16 times cosine pi divided by 4 plus sine pi divided by 4. That's the form that they want. Okay, and pi divided by 4 is indeed in between 0 and 2 pi. Okay, so we simply follow the rules that we have explained below, explained above. I will not do the second part. It's really the same idea. In this case, you just have to divide your modulus arguments and then subtract the angles from each other. Okay, so 3 pi divided by 4 minus pi divided by 2. The most important detail here, in my opinion, apart from multiplication and division of these modules of these complex numbers, is the fact that how this minus becomes plus and how this angle here becomes minus. Okay, in order to understand this, we need to go back to the notes. So this will be the solution. And remember that here we said the following. Where was it? Yes, the complex conjugate of RCIS theta is RCIS minus theta. In other words, you could also write it in this form. So, Z is equal to R cos theta, let's say, minus I times sine theta. Well, that's same thing as writing R cosine minus theta plus I times sine minus theta, and that would be equal to R of CIS minus theta. Okay. Well, let's actually see if there's a better explanation here, but I think this is sufficient, to be honest. Well, if not, we are going to have problem-solving sessions for sure, so we can focus on these little detail more. Because here, probably it's a little bit more confusing than the division and the multiplication itself. Example could be a little bit better, I would say. Okay, let's move on. Let's move on to the other form. So we have how to write a complex number in Euler's exponential form. Well, Euler's exponential form, again, is more or less the same thing. It's written in the following way. Z equals to R times e to the power of I theta. Okay, and here as well, what we need, as you can see, E is the constant E that we don't really have to find, of course. We just leave it as it is. R is our modulus argument, and the theta is our argument, and that's all. And that's all. So simply you can find your modulus of your complex modulus argument of your complex number, and then argument of your complex number, and then simply write this expression. Okay. So how do we multiply and divide complex numbers in Euler's form? Well, when you multiply, again, you multiply your modulus arguments, a simple multiplication between two numbers, and then you add the angles. For the division, you divide the modulus arguments as usual, as dividing like two numbers, and subtract the angles from each other. Okay, it's pretty much analogous to what we had in the polar form. Okay, and that would be all for the multiplication and division. Let's see another example. So there you go. Work the example. Consider the example complex number of z equals to 2e to the power of p divided by 3i. Calculate z to the power 2, giving your answer in the form of r times e to the power I theta. It's very difficult to pronounce these things too fast, so I will be slow. So how do we do this? How do we find z squared? It means just multiplying this thing by itself one more time. Perfect, which means I just have to multiply modulus arguments. I did that. 2 times 2 is 4. And since I'm multiplying, that means to add the angles. Okay, p divided by 3 plus p divided by 3 is 2 pi divided by 3 plus pi divided by 3 is 2 pi divided by 3. And that's all. And that would be your overall answer. Of course, it's better to write 2 next to the pi so that you have 2 pi divided by 3 times I. It's quite simple. Okay. Let's move on. Converting from Cartesian form to modulus argument polar form. So this is your base form, let's say. This is your Cartesian form. This is your polar form, and this is your Euler's form, right? Also, don't forget that there's a little CIS form here, which is also polar form, but it's just abbreviated way. So how do we convert from Cartesian form to the polar form? Okay, to convert from Cartesian form to modulus argument, well, we need to find our modulus. How do we do this? We find our modulus, and how it's found? Well, you take the square of A and the square of B, and then take the square root of the sum. That's your modulus argument. How do you find the angle? Either it's given or you have to use your Argand diagram, find the point to find your complex number, and then find the angle. Okay, let's see if this is your complex number, then you draw your vector, and then you find this angle. Okay, and that would be your argument. Okay, converting from now from modulus argument polar form or exponential form to the Cartesian form. So this way, from Cartesian to polar or the Euler's form is kind of more complex compared to the other way around. So if you are required to convert this to Cartesian or this to Cartesian form, then it's much simpler. Why? Because all you have to do is to open them up. Open them up in the terms of the opening brackets. If you are giving a given polar form as you have here, right? All you have to do is open up the brackets, so r times cosine theta and r times I sine theta, and then evaluate the cosine and the sine on these angles, and then basically have your simplified answer. Let's say, for example, you have, well, we have probably example here. Okay, nope. Yep, we can do, or I can give you another example myself. Let's say that you have 2 times cosine pi plus I times sine pi, right? So how do I convert this to the Cartesian form? Well, I open this up, then I will have 2 cosine pi plus 2 times I times sine pi. So what's cosine pi? It's -1, so you have -2 here from here. What's sine pi? It's 0, so from here you will get 0. So the answer is -2. Okay. If you have different angle, then you use that angle. Let's say that if you have pi divided by 2, then you evaluate the cosine at that angle and the sine at that angle, and then you simply simplify your answer, and then you have your Cartesian form. If you are given Euler's form, right? If you are given something something like this, then you convert this to polar form first, which is very easy because you have your modulus argument and you have your argument as well. So you can simply write your polar form because you have both information given to you, right? You just have to write cosine and the sine, that's all. And then from here, you convert back to the Cartesian form. So converting from polar and the Euler's form to the Cartesian form is quite straightforward. You open the bracket and that's it, and simplify. Converting from Cartesian to Euler's form or the polar form is a little bit more complex compared to the other way around because you have to find the angle. And that's all. Okay. And that brings us to the end of this lecture. So this was pretty short, I guess. And that basically summarizes all of the forms that we have for complex numbers. Again, we have the Cartesian form, which is the standard form. We have the polar form where we use our r and the theta. Okay, so modulus argument and the argument. And then we have our Euler's form. Of course, we also have CIS form, which is similar to the polar form. It's just abbreviated way of writing it. And yeah, that's the summarized way. Again, the most difficult part, to be honest, here in this whole chapter is to be able to convert, as you have seen in this example, this minus here to the inside of the function. Sometimes it doesn't work so straightforward. Sometimes it does work very simply. So you have to be careful with the angles, if you get the same angle or no. Well, let's see. Okay, it's very difficult to. Well, yeah, okay. I mean, you can understand this in the following way. So what's sine pi divided by 2? Pi divided by 2 is 90 degrees, right? If you make a unit circle, then the 90 degrees is here. So you are looking at this line, right? You go anti-clockwise, right? So sine pi divided by 2 is here, which is on the y coordinate, so it's 1, right? So when you have minus at the front, it will become -1, right? So this term here will become -1. That's the value that you are looking for. But if I make it plus, so instead of writing this, if I write plus sine of minus pi divided by 2, then let's see what I will get. Well, minus pi divided by 2 means I go clockwise this time because I have a negative value here. And then I reach this line here. And since I'm looking for the sine, which means I look for the y coordinate, and this is -1 here, which is fine. But then -1 times the plus will still be -1, and that's what we were looking. So sometimes it's probably better to use the unit circle to understand if you can really convert this minus to plus, if you can put this minus inside the bracket right away or no. Usually you cannot straightforwardly do it. Really depends on the angle. But in this case you can do. Actually, I think we can prove that you can do it for all the angles, but yeah, I will not go into the detail of that. I'm not sure if that's a rule in IB, to be honest, but in order to check this out, you can simply check the unit circle, and this will make you understand the topic a little bit more in both cases, in complex numbers and also in the unit circle. Okay. Okay, so let's wrap it up, and that's all for this lecture. I hope you are happy with it. We will have a little bit of question solving and the practice questions and the past paper question solving lecture soon, and some office hours. So don't forget to join my Discord server, and don't forget to subscribe and put a like on the videos. And that's it. See you soon.